All right, so we're going to talk more about power series. And specifically what we're going to use in this video is if we look at 1 over 1 minus x, we could rewrite this. Remember that a power series is a polynomial. This can be written as an infinite polynomial, a sum from n equals 0 to infinity of x to the n. And what we want to do is we're going to start with this original, and we are going to create power series for different functions using this. So we're going to use this and make power series for other functions. And we can do this just by doing some algebra. We can multiply or divide by powers of x. We can take derivatives, or we can take integrals. And I'm actually going to combine these into one, because when you do this, you sort of use both. Integrals. All right, so let's, one other thing that I do need to state is that this is a power series, and it converges if the absolute value of x is less than 1. So its interval of convergence is from 1 to -1. So you don't have to check to see intervals of convergence, and we can use this fact. So let's say, for instance, that we have 1 over 1 minus 3x. So in this, instead of x, we have 3x. So in order to make a power series for this, every time we see x, we can just plug in 3x. So instead of into the sum, instead of having x, we're going to plug in, I don't know why I just wrote the negative, I didn't mean to. We just plug in 3x. So that would all be raised to the n. So our new power series, or our power series for this function, would be 3 to the n times x to the n. And if we wanted to look at the interval we could get, instead of x being less than 1, the absolute value of 3x would be less than 1. And so our interval for this one, x, would be in between 1/3 and -1/3. That would be our interval. So here's our power series, and here's our interval. And all I did there is just take this 3x and I plugged it into every single x in this formula to figure that out. Okay, so example. Let's look at the sum from we need a function in here. All right, so let's look at the function. 1 over 4 minus 2x cubed. Now keep in mind it's 1 over 1 minus x that's equal to the sum from n equals 0 to infinity of x to the n. So in this one, we don't have a 1, we have a 4. So I need to factor that out. If I do that, then I am left with a 1 minus 2 over 4 times x cubed. So that would be 1 over 4 times 1 minus, say, x cubed over 2. And so if we put this into the sum from 0 to infinity, instead of having x to the n, we would have x cubed over 2. So x cubed over 2 to the n. And then we also still have this 1/4 that's out in front of all of that. This 1/4 just kind of stays out in front. and we plug in the negative, or plug in x cubed over 2 in for x. When we write these out, we usually write out all the x's and then everything else separately. So this would be the sum from n equals 0 to infinity of x to the 3n divided by 4 times 2 to the n. And we could even rewrite that even further. X to the 3n divided by 2 to the n plus 2. And it's a plus 2 because 4 is equal to 2 squared. All right. And if I wanted to find the interval for this one, instead of plugging in x into that absolute value, I'd plug in x cubed over 2. And so this would be where x cubed would go from 2 to negative 2, and then we'd take the cube root. So any x from the cubed root of 2 to the cubed root of negative 2 would work. That would be our interval. So here's our power series, and here's our interval. Now another example, I'll do it in a different color on this page, would be if we wanted to find x squared over 4 minus 2x cubed. We've already found the 1 over 4 minus 2x cubed. And so we could look at this as being x squared times the sum from n equals 0 to infinity of x to the 3n divided by 2 to the n plus 2. And now what we need to do is multiply those x's together. So for this one, we can multiply those x's in now. We found an original using that function, and now we would have x to the 3n plus 2 because of that new exponent on that x squared over 2 to the n plus 2. So the trick on this one that's in blue, multiply by a power of x. The trick on the one before that is you had to do some algebra. Had to do some algebra to get the 1 minus whatever we want to call x this time, which happened to be x cubed over 2, and then we plugged that in. All right, so one more example here. If we want to find a power series for the natural log of 2 minus x. Now, notice that if I take a derivative of natural log, I get 1 over 2 minus x and then times a negative, and that's close to the function. I'll write it up here again. 1 over 1 minus x is equal to the sum. It starts at 0 of x to the n. It's close, but I have a 2, so I need to factor that 2 out. So negative 1, if I factor out the 2, I'll be left with 1 minus x over 2. So now I can rewrite that as a sum. Sum from n equals 0 to infinity. I've got a negative 1/2 in there. And then I'd have not an x to an n, but an x over 2 to an n. That sum is equal to the sum from n equals 0 to infinity of, I just have a negative out there, x to the n. In the denominator I have a 2n, and that's multiplied by a 2, so that would be an n plus 1. All right, now to get from natural log to that function, I took a derivative, and I found a sum for that derivative. Now I need to go back, and so I need to undo that derivative and integrate. Now when we integrate, so like say we take the integral of x squared, that's x cubed over 3. Right, we add 1 and divide by that number for the x's. Everything else is a constant in this. So I've got my sum. The negative is a constant. The 2 to the n plus 1 is a constant. I'm only integrating the x's. So only for the x's am I going to add 1, and then I'm going to divide by that number. And we're done. All right, I'm going to summarize this one more time. So for natural log, I took a derivative to make it look like the function that I know the power series for. I had to do a little bit of algebra to change that into a power series, and then I integrated that power series by just adding 1 to the exponent of x and dividing by that number. If we were to look at the interval, derivatives and integrals make absolutely no difference. For the interval, you would plug in x over 2 because that's what you plugged in from the function to the power series. And so the interval would be in between 2 and negative 2. So derivatives and integrals don't make any difference on the interval at all. Okay, so we could have done something similar if we could have integrated to get to this function. We then would have took a derivative of the sum. All right, so this whole derivative and then integrate is another trick. Oh, I just forgot something. I'm not done yet. When you integrate, you get a plus c. You do get a plus c. Now, when I'm going to find that plus c, when x is equal to 0, I get natural log of 2. So if I plug in x equals 0 into this sum, I get the sum from n equals 0 to infinity of 0 divided by, I don't even care because they're just some numbers, and we'll get 0 plus c. So all of that is 0. And so c is equal to natural log of 2. And so really, this sum right here should be the entire sum. Let's see if I can erase a little bit in here. I can't. I can erase that. The entire sum plus the natural log of 2. So yeah, when you integrate, you do get a constant as well, and you can find that constant by plugging in. Usually x equals 0 is the easiest. Okay, so those were some things of ways to manipulate a known power series to get a different one.